right, so today we're going to move on from factors and start looking at factor trees and prime factorizations. So in a factor tree, we're going to break down a number as far down as we can using its factors in pairs. So we need two factors of this number to break it down. So two numbers that we multiply together to get that number. For the number 90, we might think of 9 and 10. Because I see there is a 0 at the end of this number, that means it's divisible by 10, and 9 times 10 is going to get me 90. And then we keep breaking these numbers down as far as we can go. So there are other factors of 9 also. I could get 9 by multiplying 3 times 3. I cannot break 3 down any further because 1 times 3 is 3, but that doesn't really help me. And 2 will not go into 3. So there are no other factors of the number 3, just 1 and 3. That means 3 is a prime number. So that's the end of my tree here. I'm going to go ahead and just circle this to say, hey, I'm done at this point. That's the last branch on this part of the tree. Same thing with this 3. Can we break the 10 down any further? Yeah, that's an even number. It's divisible by 2 and 5. 2 is also a prime number, so we're going to circle that one. The only numbers that go into 2 are 1 and 2 evenly. Then 5 is another prime. 2 will not go into 5, neither will 3, neither will 4. So 5 has to be prime. And that ends my factor tree right there. A couple of important prime numbers you might want to think about. 2 is important as it is the only even prime number. All other prime numbers are odd. And then these are just the first several as we go up counting. 3, 5, 7, 11, 13, 17, 19, 23, 29. There's an infinite number of prime numbers out there, but those might be helpful to know, especially those early ones, 2, 3, 5, 7, 11. And then what we're going to be looking at today primarily is prime factorization, an expression of a prime or of a number as a product of its prime factors. So the prime factors of 90 are 3, 3, 2, and 5. So when I write prime factorization, I like to write them in order, but the prime factorization of 90 then is 2 times 3 times 3 times 5. So if I multiply those numbers together, 2 times 3 times 3 times 5, we will get 90. So you can break down a number into a unique representation of its prime factors, and this is going to be helpful in the future and a couple of other things we'll look at. You might be worried about, what if I didn't see that 9 and 10 were factors of 90? What if I chose 2 and something because I saw that 90 was an even number? It will still work out just fine. If you instead started knowing that 90 is divisible by 2, then you could do 90 divided by 2. See that that's 45. 2 is prime, so you could circle it here. 45 is divisible by 5. 5 times 9. 9 can be broken down into 3 and 3. And you still have a result of the same prime factors, 2, 3, 3, 5. So the tree looks different, but as long as you are properly doing your factors, you will come out with the same prime factorization. So let's just do a couple more examples and then we can wrap it up for today. So next, let's see about the prime factorization of 60. So I like to do bigger numbers if I can see them. So for 60, we might think 6 and 10. We can break 6 down further into 2 and 3. Those are both prime numbers. We can break 10 down further into 2 times 5. Those are also both prime numbers. So then I can rewrite 60 as a prime factorization of 2 times 2 times 3 times 5. And then I wanted to do one more special example. So the number 53. If we want to break down 53, this number is a little bit interesting because it's not even, so 2 will not go into it. So if I try to make my factor tree, I cannot split it into 2 and another integer. So then what about 3? Well, 5 plus 3 is 8. 8's not divisible by 3. So 53 is not divisible by 3. Can't divide 4 into 53. I can't divide 5 into 53. Can't divide 6 into 53 or 7. Maybe you want to double check on 7 there. 53 divided by 7, that doesn't work either. 53 divided by 8 doesn't work. Now these numbers are getting smaller and smaller, and I already know those smaller numbers aren't factors. So 53 is a bigger prime number, which means its prime factorization is just 53. You can't break it down any smaller. So if you attempt to make a factor tree for a number and you cannot break it down any further, that number itself is prime. And that should do us pretty well for factor trees and prime factorization.